Today, we will present you a blind test demonstration. So we will have a live connection with the wind tunnel. So at this point, let me introduce Patricia and two colleagues, Peng-Chuan and Ravi, who are waiting in the wind tunnel because of the live demonstration. So the next generation of intelligent aerospace materials will be able to feel, think, and react in real time based on high resolution, state sensing, awareness, and structural health monitoring technologies. Now, in the structures and composites lab, we believe that if we reach a specific level of maturity that is required, we will be also capable of achieving what we like to call fly-by-feel. And fly-by-feel is a completely autonomous flight as inspired by biological systems. Now, in our lab, we have been working on various technologies, starting from bio-inspired sensor networks, signal processing, structural health monitoring, diagnosis and prognostics, along with a complete system integration. Now, actually, the technology that we believe may enable this fly-by-feel concept are the bio-inspired stretchable sensor networks. These networks comprise of microsensors distributed that are fabricated on a 4x4-inch wafer, and then they can be released and expanded to cover a large area. In addition, these networks have a very specific advantage. They can be either embedded inside the layup of composite materials, but also they can be mounted on the surface of metallic structures. So actually, in this demo, we will present you the complete integration of these technologies for a bio-inspired composite wing. In this wing, we have embedded 148 sensors inside the composite layup, and we have strain gauges to monitor the strain in real time, piezoelectric sensors for active and passive sensing structural health monitoring, as well as vibration monitoring, and also we have temperature sensors to monitor the external environment. So at this point, I think we can connect with the wind tunnel facility where we perform a blind test. Let me introduce my colleagues Peng-Chuan and Ravi. So hi guys.
Hi everyone.
So Peng-Chuan and Ravi will controlling the wind tunnel and the wing, and at the same time we'll be collecting and analyzing the data, trying to find out if what is happening in the wind tunnel also is the same with what our integrated software demonstrates. So I think at this point we can see the wind tunnel. So this is the wing. It's a close-up of the wing. The top layer is fiberglass, but the bottom layers are carbon fibers. And here you can see a sticky tape, this yellow tape, that is used actually to simulate local damage. So we will use our active sensing structural health monitoring approach to detect and localize damage. So I think at this point, we can start the test. So
okay, so now I will turn on the wind tunnel, and I'll reset the angle of attack to around 5 degrees.
Okay. So we can see that we have the tapes that are vibrating because of the airflow. We can see the airspeed that increases, and at this point, the airspeed is a direct input from the wind tunnel. Then we can see the angle of attack actually that is estimated using our signal processing approaches and the strain gauge distribution. At the same time, we can see the lift monitoring, again using the strain gauges that we have embedded inside the composite layup, and we can see that at this time we're in the green range. So this is kind of the safe range for this UAV to have the lift without any flutter or vibration. Below, we can see the flutter monitoring index. So this is actually an index that we have come up with to monitor the dangerous vibration and flutter of the wing. And finally, we have a real-time integration with a high-fidelity numerical model when we are having the lift as the input, and based on that, we can also calculate in real time, in a static manner though, the stress distribution on the wing.
So I've now further increased angle of attack to around 10 degrees.
So we can see that Peng-Chuan is increasing the angle of attack. At the same time, we can see that indeed, we have 10 degrees using the strain gauges. The lift has increased, so right now we're getting to the yellow stage, which is kind of, we're approaching stall. And again, we don't have any flutter, which is also evident by checking the video feed from the wind tunnel.
So now I'll further increase angle of attack to stall.
So again, we can see immediately that we have detected stall. The lift has gone to 0, has dropped to 0. Also, we can see that we have a high vibration on the left-hand side because of the stall vibration. And this is also evident from the flutter monitoring index, where we are in the yellow range. Thank you, Peng Chuan.
Okay, sure. Now we set the angle of attack around 5 degrees towards the SHM on the wing.
So we're going back to 5 degrees. Indeed, immediately we have this indication, and we can try to have the active sensing SHM, so we can open the corresponding graphical user interface. This is great. And now we can get signals in real time, so we're using the piezoelectric sensors as an active mode, but at the same time we're getting the signal from the remaining PZTs. And we can see immediately that we have detected and located damage. So I think to summarize, we demonstrated the integration of our bar-inspired sensor networks along with the signal processing and diagnostic approaches for this smart composite wing. Thank you.
Thank you very much.